Let's start with the image almost everyone has in mind, a wormhole as a glowing portal in space. You fly in on one side, pop out somewhere else, and skip an absurd amount of distance like the universe suddenly forgot how far apart things are. That image is useful, but it's also misleading. A wormhole is not really a portal in the sci-fi sense. A better way to think about it is as a shortcut through spacetime. Imagine two distant points on a sheet of paper. If you travel across the surface, the path is long, but if you fold the paper so those points touch, the distance becomes tiny. That is the core idea, not breaking space, but connecting it differently. That's why wormholes are so fascinating. They don't require faster than light motion through normal space. In principle, they change the route itself. So where did this idea come from? The first famous version came from general relativity. Einstein's equations allow strange geometries, where spacetime can curve and connect in non-obvious ways. In 1935, Einstein and Nathan-Rosen described a structure now called the Einstein-Rosen bridge. It linked two regions of spacetime in the math, and it became one of the earliest wormhole-like ideas in physics. That sounds exciting, but there's a catch. The original Einstein-Rosen bridge is not the nice, stable tunnel that science fiction loves. It's more like a mathematical connection that pinches off too quickly for anything to cross. The bridge is there in the equations, but not as a practical doorway. And that leads to the biggest problem. A normal wormhole wants to collapse. The narrow middle of the tunnel, usually called the throat, is unstable. Gravity keeps trying to squeeze it shut. In most simple models, the throat closes too fast for light, let alone a spaceship, to make it through. So even if a wormhole could form, an ordinary one is not expected to stay open long enough to be useful. That's the central obstacle, not finding a wormhole. Keeping one open. And this is where the physics gets weird. To hold a traversable wormhole open, you need something that pushes back against that collapse in a very unusual way. In many theoretical models, that means some form of exotic matter with negative energy density, or at least stress energy that behaves nothing like normal matter. That does not mean antimatter. Antimatter still has positive mass energy and still responds to gravity in the usual way. Exotic matter means something stranger, a configuration that could create the kind of gravitational effect needed to prop the wormhole open instead of letting it snap shut. That sounds like fantasy, but tiny negative energy effects do appear in some quantum situations, like the Casimir effect. The problem is scale. Seeing a small quantum effect in a lab is one thing. Using anything like that to stabilize a tunnel through spacetime is another level entirely. So, can you actually travel through one? Theoretical answer: maybe, in certain mathematical models. Practical answer: we have no evidence that traversable wormholes exist, no known way to create one, and no known source of exotic matter in anything like the amount you'd need. So wormholes are not ruled out as pure geometry, but they are extremely far from engineering. Even if one existed, there would still be brutal questions. Are the tidal forces survivable? Is the throat stable while matter passes through? Does radiation build up near the entrance? Does the structure stay open long enough, or collapse the moment anything tries to cross? These are the difference between shortcut through spacetime and instant cosmic death tunnel. This is where sci-fi usually takes over. Movies and games love wormholes because they are the cleanest possible shortcut. Step in here, come out light years away, and the story keeps moving. Visually, they look like glowing rings, tunnels, or rippling portals. That makes sense for storytelling, but real physics is much less friendly. Interstellar is a good example. The movie treats the wormhole near Saturn as a traversable shortcut, and that part reflects the basic idea surprisingly well. It isn't warp speed, it's geometry. But the film skips the hardest parts, especially the stability problem and the exotic matter problem. It gets the vibe right, not the engineering. And then there's the bonus idea that makes wormholes even more dangerous to your brain: time travel. If you had a traversable wormhole and somehow moved one mouth at high speed or placed it in a stronger gravitational field, time could pass differently for that mouth compared to the other. That's just time dilation. But if the two mouths remain connected while becoming desynchronized in outside time, stepping through could, in principle, send you into the other mouth's past or future relative to the outside universe. That's why wormholes show up in time travel discussions, not because they are magic time doors, but because once you combine shortcuts through spacetime with relativity, causality starts to look very nervous. So what's the takeaway? A wormhole is not really a portal. It's a hypothetical shortcut through spacetime. General relativity allows wormhole-like geometries, but ordinary versions collapse too quickly to cross. To keep one open, you likely need exotic matter with extremely strange properties. That makes traversable wormholes possible on paper, but wildly unrealistic in practice. Sci-fi gets the shortcut idea right, but skips almost all the impossible parts. And if traversable wormholes did exist, they might not just connect distant places. They could also interfere with time itself. That's wormholes, one of the coolest ideas in physics, and one of the least cooperative. If this helped, like and subscribe for more fast space explainers and comment. If you found a wormhole tomorrow, would you go in?